Okay, good morning. All right, let's take a look at number one here. This is a just a dissolving, a solid in water problem, and we're going to calculate the amount of heat that's released, and then see if we can then figure out the enthalpy of solution. So that's the final, objective ultimately in these kinds of problems. Okay, so let's take a look. So it says, imagine that we dissolve 20 grams of sodium hydroxide in 270.0 milliliters of water. During the dissolving process, the water temperature rises from 23 to 42.5 degrees. Okay, so clearly dissolving sodium hydroxide in water is an exothermic process. It has to be releasing heat into the solution in order to warm it up. So, part A. Okay, so it says how much energy was transferred in joules during the dissolving process. Okay, well, this is where we use good old MC delta T, right? Um, and So the mass, okay, so the first thing is we need to figure out what is the mass. And so we have 20 grams of sodium hydroxide, and then we have, the solvent is 270 milliliters of water. So the thing that is heating up is the solution. So it's the combination of the sodium hydroxide and the water, right? And so we need to combine the masses of both of these substances in our MC delta T equation. Okay, so we know that the density of water is 1 gram per milliliter. So if we have 270 milliliters, that's 270 grams. And we add that to the 20 grams of solute, right? So the sodium hydroxide is the solute. And so the total is 290. So that's 290.0 grams. And then we multiply that by the specific heat, which is, we're going to use the approximation that the specific heat is 4.18 joules per grams degrees Celsius, just like in pure water. And then the delta T, we just take the final temperature, 42.5, and subtract the initial temperature, which is 23.0, and you should get 19.5 degrees. Okay. And when you crank all that out, it's going to be quite a lot of joules, 23,638 joules, okay, which is equal to 23.6 kilojoules. Okay, so when you convert that to kilojoules, you should get that. Okay, so that's how we calculate the energy transfer when there's a temperature change. Okay, so we'll keep this energy value, 23.6 kilojoules. We'll keep that in our back pocket, and we need to go on now and now calculate the enthalpy of solution for sodium hydroxide in kilojoules per mole. All right, so the trick here is the figuring out the moles, right? That's the part B part of this process is figuring out, okay, if we have 20 grams of sodium hydroxide, how many moles is that? All right, so down here, I'll just show. So the moles is 20 grams of the sodium hydroxide, and we multiply that by 1 mole on top over the molar mass. Okay, so the molar mass of sodium hydroxide, sodium's 23, right? 23.0. And then the oxygen and the hydrogen together make 17.0. And so the total is 40 grams. And you don't even have to pull out your calculator for this. You can see that it's exactly 1/2 or 0.500 moles. Okay, so in the final step, what we do to calculate the enthalpy of solution, so that's supposed to be a delta H with the subscript SOL, and the SOL means solution. So all you got to do is take the kilojoules that we calculated, which was 23.6 kilojoules, and divide it by the number of moles of sodium hydroxide that led to this amount of heat being released. And when that all comes out of the wash, you should get 47.2, and that's kJ over mol, right? Kilojoules per mole. And finally, we got to make sure that we get the sign right. So before you submit any kind of a delta H value, you've got to make sure that you associate the right sign with it. Okay, so as we said, because the temperature went up, we know that this was an exothermic process. And we know that exothermic processes are associated with negative signs. All right, so that would be your final answer, negative 47.2 kilojoules per mole. Okay, so now let's go on to the next one. Okay, now this one is obviously a reaction. So this is not simply dissolving some compound in water. This is taking two substances. In this case, we have potassium hydroxide, and it's reacting with nitric acid. Okay, so it's an acid-base reaction, right? That's nitric acid. This is potassium hydroxide. So it's an acid-base reaction. Okay, so let's take a look. It says that they take 50 mils of a 2.5 molar solution of nitric acid, and they combine it with 50 milliliters of a 2.5 molar potassium hydroxide solution. Okay, both solutions have an initial temperature of 22 degrees, and at the end of the reaction, the temperature of the combined solution reaches 39.2 degrees. So clearly another exothermic reaction, right? The temperature went up by, over 17 degrees. Okay, so part A, how much energy was transferred? Okay, so let's see if we can figure out the mass value. What was the mass of the total solution after they were combined? Well, you have 50 milliliters of the acid and 50 milliliters of the base. And since, again, we're assuming that these solutions have densities that are very close to the density of water, we'll assume 1 gram per mil. So we got 50 grams here, 50 grams there. Add those together, and you get 100 grams. We, unless told otherwise, we're going to assume that the density of these solutions is 1 gram per mil, and that the specific heat values are 4.18 joule per gram degrees Celsius. Okay, so we went up 17.2 degrees Celsius. And let me do this down here. And when you do that calculation, you should get 7,190 joules, which is 7.19 kilojoules. Okay, so we've got the energy part. Now, let's talk about the figuring out the enthalpy of reaction. Okay, so it's going to be in kilojoules per mole. So we've got the kilojoules part, right? So we got that. But now we got to figure out how many moles of the substances actually reacted in this reaction. Okay, so I'm going to put a little line under each reactant, and we're going to, once we figure out the moles, we'll put the mole values underneath each substance here. And then that'll help us figure out how many moles of products we're going to make. All right, so part B. So this is where you got to remember that molarity is equal to moles divided by liters of solution. Okay, so moles of solute. Let me be precise about this. It's the moles of the solute, the stuff dissolved in the water, divided by the liters of solution. And then if you simply rearrange that expression, you'll get molarity times liters, which is volume, right? And so that's basically N equals M times V. Okay, so let me go to the next page here. So N moles equals molarity times volume. And what we saw here was that we were working with 2.50 molar solutions of each, right? So both reactants are 2.50 moles per liter. So moles per liter. And again, I always, even when it says 2.50, big M, I unpack this. I unpack the molar symbol into moles per liter when I do these calculations. And then 50 milliliters, right? 50 mils, that's 0.0500 liters when you convert that to liters. Okay, so that's the other thing. You gotta have you gotta have the volumes in liters. Okay, so you multiply these guys together, and you're going to get 0.125 moles. Okay, so hopefully that came out okay for you guys. Now, the thing that you notice is because the volume and the molarity of both reactants are identical, then we can assume that the moles of the nitric acid are equal to the moles of the potassium hydroxide, which we now know is 0.125 moles. Okay. Now, back to the chemical equation. Let me clean things up just a little bit here. Okay, so if we go back to the chemical equation, now we can label each reactant with the number of moles that are reacting. Now, guys, I'm being very methodical here. Okay, so if some of you may be kind of chafing at how slow I'm going, but I'm just trying to make sure that I explain every single step. And you can always pause the video. You can fast forward. You can go back and re-listen to any of this if you need to. But I'm just trying to lay it all out here. Okay, now if you look at the stoichiometry of this chemical equation, it is balanced, first of all, and you can see that everything is 1-to-1, right? And so, and you've been given a 1-to-1 mole ratio of reactants. So if you're reacting 0.125 of each reactant, then how many moles of product are you going to get? And if you're thinking 0.125 of each, you are exactly right. Okay, it's 0.125 all across the board. So this is indeed the value that we need to use when we calculate the kilojoules per mole. So now we're in a position to do that. All right, let me change this back to green. All right, so our enthalpy of reaction is, we'll take the kilojoule value that we calculated in part A, and now we're going to divide that by the number of moles that reacted to produce that amount of energy. And when you do the calculation, you should get 57.5, and that's kilojoules on top over moles on the bottom. And since it's an exothermic reaction, you got to have that negative sign in front. Okay? All right. Thank you very much, guys. I'll talk to you later.